Good morning, everyone. Imagine if we could make wireless networks smarter without requiring additional spectrum. Our research tries to address this key question that can machine learning help new wireless systems share spectrum with the current users? I'll now motivate the need for spectrum sharing, present our proposed solutions, and explain why it matters for future 6G networks. Wireless spectrum is extremely expensive. Indian telecom operators spent around 1.5 lakh crores for 5G spectrum. This investment impacts mobile tariffs in long term. Spectrum is also limited, so we need to use the existing spectrum efficiently. To address the above issue, spectrum sharing is one of the promising solutions that is part of different wireless standards. Here, new technologies can coexist in the same frequency bands as the existing users. New users are referred as secondary users, and the existing users are referred as primary users. This spectrum sharing enables efficient use of the limited spectrum. We focus on underlay mode of spectrum sharing, in which the low priority secondary user transmits simultaneously in the same frequency band as the high priority primary user. Hence, secondary transmissions will cause interference to the primary. Controlling this interference is crucial, as new wireless systems must communicate without disturbing the primary licensed user. Antenna selection is one of the multiple antenna techniques that can control the interference to the primary. In it, the secondary transmitter equipped with multiple antennas and one radio frequency chain selects one of the antennas based on the channel conditions and dynamically switches to the radio frequency chain available. In spectrum sharing, antenna selection should consider interference to the primary as well. In our secondary system, the transmitter is equipped with L antennas and one radio frequency chain. It selects one antenna index S to communicate to the secondary receiver. As it shares spectrum with the primary, its transmissions cause interference at the primary receiver. Our goal is to select an antenna S at the secondary transmitter that reduces errors at the secondary receiver and ensures interference at the primary receiver is below a threshold. In the conventional approach, the optimal antenna index S star is the one that minimizes the metric inside the braces. The first term is an error probability term that requires integration, and the penalty factor lambda needs solving an equation numerically. Although this conventional approach is optimal, it is too slow for real-time wireless systems. To reduce the complexity, we proposed two different solutions based on deep neural networks. First solution develops a classification model based on supervised learning, and the second one develops a regression model with model-based learning. They are 10,000 times faster than the conventional approach. The classification model uses a supervised learning approach to take channel information and interference threshold as inputs and directly predicts the antenna index S, which can take values from 1 to L. This model needs to be retrained for any change in the parameters such as number of antennas or thresholds. Different from solution 1, the solution 2 develops a regression model using model-based learning. Here, for a given power, number of antennas, and threshold value, the model predicts the penalty factor lambda that is substituted in the conventional approach metric. Here, an approximate error probability with no integrations is used to select the antenna index to further reduce the complexity. This exploits the structure of the optimal selection rule and need not be retrained for any change in the system parameters. Here, the first plot shows that both machine learning approaches achieve almost the same error performance as the conventional approach. The second plot shows that both models satisfy the interference constraint. So, both the proposed approaches perform well while satisfying the interference constraint. The most important result is speed. The conventional approach takes several seconds and increases with the number of antennas due to integrations. The proposed methods, however, needs only about 8 milliseconds and are independent of number of antennas, making real-time implementation practical. To conclude, we have shown that proposed machine learning solutions perform well with significantly lower computational time, enabling efficient use of expensive spectrum and reducing future deployment costs and supporting AI native 6G networks. Instead of buying more spectrum, we can make wireless networks smarter. Thank you.